In this video, we will discuss about how the given switching function can be designed using programmable logic array. In a previous video, we have discussed about PROM, where PROM consists of n to 2 power n decoder and m number of OR gates, where n to 2 power n decoder having 2 power n number of AND gates. To design our required logic, among the 2 power n number of AND gates, we may use few number of AND gates. In that point of view, hardware utilization is poor. So 2 power n number of AND gates are replaced with very few number of AND gates. Concept wise, PROM and PLA both are same. The only difference is 2 power n number of AND gates. That means decoder replaced with some array of AND gates. Right. So here we are taking the one simple example. How that given switching function or combinational circuit using PLA we will discuss now. Design a combinational circuit by using PLA. Here the combinational circuit having two outputs, F1 and F2. First step, simplify the F1 and F2. Get the minimized SOP for given output functions in normal form and complement form. That is the first step. So here F1 is sum of minterms of 3, 5, 7. You have to minimize the given. So 3 variable K-map you have to consider. 3, 5, 7 filled with logic 1. Remaining cells are filled with logic 0. Similarly F2. F2 equal to sum of minterms of 4, 5, 7. 4, 5, 7 filled with logic 1, remaining all are filled with logic 0. First, minimize the F1 by grouping ones. Right? To group the ones, two pairs are possible. This is the one pair, this is the another pair. For this, simplified expression is A, C. For this pair, simplified expression is BC. So this is the F1 in normal form. Again find F1 in complemented form, that is F1 bar. To get the F1 bar, we have to group the zeros. So to cover the all 5 zeros, grouping choice is 1 quad, 4 cells and 1 overlapping pair possible. For this quad, common term is C bar. For this pair, expression is A bar, B bar. I think all are familiar with K-map, right? So then about F2. To group the ones, two pairs are possible, A B bar plus AC. Then to get the complement of the F2, that is F2 bar, we have to group the zeros. So to cover the zeros, 1 quad, and one pair. For the quad, expression is A bar. For the pair, expression is B C bar. So this is the first step. So initially you have to find the simplified expressions by using K-map in both form. That is normal form, that is F1 and F2, that means by grouping of ones. Then you have to find the F1 bar and F2 bar. Later you have to identify in which combination we can get the less number of distinct product terms. Less number of distinct product terms means for design we may consider F1 and F2 both are in true form, that is normal form, or we may consider F1 in true form, normal form, F2 in complement form, or F1 in complement form, F2 in true form. F1 and F2 both are in complement form, right? So how many choices are possible to design the logic? We are having how many functions? 2 output functions. We may consider F1 and F2 both are in true form. F1 true form, F2 in complement form. F1 complement form, F2 true form. Then F1 and F2 both are considered as a complemented form, right? In every choice, how many distinguished product terms are taken place? For example, F1 and F2 take. F1 and F2 take. Here how many product terms are there? AC and BC. Then AB bar and AC. So total how many products? 4 products we are having. AC, BC, AB bar, AC. But how many distinct product terms are present? Right? Here AC repeated. In F1 and F2, AC repeated. So AC, BC, AB bar. So total how many distinct product terms are there? 3. What are those? AC, BC, AB bar. AC already covered, repeated, right? So now F1 in true form, right? F2 complement form. So total how many products? How many distinct products? 1, 2, 3, 4. All are distinct, no repeated, right? Next, F1 bar complement, F2 true form. Here how many products? 1, 2, 3, 4. 4 are distinct product terms. Next, F1 bar in complement form, F2 bar in complement form taken. So here also how many products? 2, 3, 4. 4 are distinct product terms, right? So in which choice we have to cover F1 and F2? We have to design F1 and F2. So for our convenience, we may take the F1 and F2 in both are true forms, right? One in true, another one in complement, or both are in complement. So these are the possible choices. In which choice we are having the less number of distinct product terms? In which choice we are having the distinct product terms? Less number of distinct product terms. F1 taken in true form, F2 also taken in true form. So list out distinct product terms. What are the distinct product terms? First one is the AC, second one is BC, third one is AB bar. So in F1 and F2, these 3 are the distinct product terms. In the remaining combinations, we are having the 4 product terms. So you have to select in which combination less number of distinct product terms are present. So in design, if you consider less number of distinct product terms, which replied in less number of AND gates. Why? Because every product can be realized by AND gate. So we are going for the less number of products. So less number of AND gates we can get. So the cost of the programmable logic device will reduced. So this is the second step. You have to find in which combination less number of distinct product terms are present, and we have to list out distinct product terms. Right. Then you have to prepare PLA programming table. So first product term AC, second product term BC, third product term AB bar. So this table is very simple. Just you have to list out inputs and outputs. Right. In this product term, A presented in normal form, so put 1. B not present in the product term, so put dash. C presenting in normal form, so put 1, right? So if variable, presence of variable in normal, you have to represent it with 1. In complement, you have to represent it with 0. Not present, if that variable is not present, you have to represent it with dash, right? So here this is the product. In this product only 2 variables are there, A and C. 2 variables are in normal form, so A and C, in place of A and C you have to put 1. B not there, so you have to put a dash. Similarly BC, B and C both are in normal, A not present, AB bar, A in normal form, B in complement form, so that's why in the place of B you have to put 0. C not there, so you have to put a dash, right? Then outputs, inputs you have to list out, then presence of variables you have to mention here. Then outputs, what are the outputs? F1 and F2. F1 covers, what is the Boolean expression for F1? Once observe the F1 expression. F1 taken in normal form, F2 also taken in normal form. F1 covers AC and BC. F1 covers product 1 and product 2. F1 covers AC and BC. It not covers AB bar. So if not covers, put a dash. If covers, put a 1. So got the point? Very simple, right? So F1 is a one simplified Boolean expression. F2 is a one simplified Boolean expression, right? So we are listed out all distinct products in F1 and F2. Some products covered by the F1, some products are covered by the F2. So if the product covered by the F1, you have to place 1. If not covered, you have to place dash. So what is the expression for F2? F2 equal to, if you observe the F2 expression, what is the F2 expression? AB bar plus AC. AB bar plus AC. So AC covered by the F2, AB bar covered by the F2. So to get the less number of distinct product terms, F1 taken in true form, F2 taken in true form. So you have to prepare PLA programming table. So this preparation of the table is somewhat convenient to design or to program the taken PLA to your logic. So that's why initially we are preparing the PLA programming table, right? So now we are consider how many 3 products we are having. So how many AND gates you have to consider? 3 AND gates you have to consider. 1 AND gate to get AC, BC and AB bar, right? So what are the inputs? A, B, C are the inputs. Every AND gate having, let n is the number of inputs, right? So these are the inputs. Let this is the n. Every AND gate having 2 power n number of switches. Every AND gate having 2 power n number of 2 power n, right? Sorry, 2n number of switches, not 2 power n, 2n number of 2 into n number of switches we are having. So three inputs we're having A, B, C, A line, B line, C line. Next A bar, B bar, C bar. Draw one horizontal line which joins all vertical lines. Every joining, every intersection representing the electrical fuse. Or you may draw like this also, right? Draw the AND gate. How many fuses are there? One fuse for A, one fuse for A bar, one fuse for B, another fuse for B bar, next for C, then C bar. Like that also you can represent. But to draw this type of symbolic representation is not that much convenient. So that's why simple notation I am following. Just to take one AND gate, draw one horizontal line which joins three lines for normal, three lines for complement. So these AND gate having 2n number of fuses or switches, right? So here n is 3, so that's why 2 into 3. This AND gate having how many switches? 6 switches. Like that, how many AND gates we are having? 3 AND gates. Every AND gate having the 6 switches, 6 fuses, right? So you have to make a fuse connection or you have to make a switch connection. So first AND gate for AC, second AND gate to get BC, third AND gate to get A, B bar. So which fuses you have to make a connection? A, so put a into mark, then C. This is the way to represent how we are programming array of AND gates. Next BC, right? B line, C line. You have to consider this is the input line for this AND gate. So joining intersection of the B line and the C line with input line of AND gate, you have to put a cross mark. Next, similarly, A, B bar we require, right? A line, B bar line, you have to put a tick mark. So very simple. Now F1 and F2 you have to design. These are the distinct product terms are generated. Then you have to generate actual outputs F1 and F2. So for that we require the OR gates. So 3 products. So every OR gate consists of 3 fuses. At maximum 3 fuses are there. One fuse for AC, one fuse for BC, another fuse for AB bar. So this joining representing the fuse, right? Here also 3 fuses you have to consider. Like this you have to draw. Now by observing the expression table, F1 taken in true form, or sometimes to get the distinct product terms, F1 and F2 may be taken in different forms instead of normal form. So such a cases you have to get these arrangement. So we may take the F1 bar to get the distinct product terms, but we require the F1 to design. So such a cases F1 bar passed with complement, then we can get the F1, right? Such a cases these NOT gates are helpful. To get the less number of distinct product terms, sometimes we may take the complemented outputs. So, but we require the normal outputs to realize. Such a cases, these NOT gates we have to use. Taken is complemented output to get the less number of distinct product terms, right? NOT gate, if you are consider, take an expression complement, that is passed through NOT gate. So we can get the normal expression, right? So such a cases, these arrangement is preferable. So what is the F1 here? F1 and F2 are taken in which form? True form. F1 in true form, F2 also true form. So that's why make a fuse connection. Direct, no need to pass the signal through NOT gate. Direct fuse connection. So that's why signal is passed through short circuit instead of through NOT gates, right? Here we are taking the F1, so as it is F1 is passed. Right, to get the F1, what are the AND gates are required? AC, so put a cross mark, then BC. Next, to get the F2, AC and AB bar. Boolean expressions of F1 and F2 or table you can consider. What is the F1? F1 is F1 covers AC and BC, so those fuses you have to make a connection. And then F2 covers AC and AB bar, so those fuses you have to make a connection. This is the way to design the PLA. So quickly we can consider one more example. Here example is F1 ABC equal to sum of minterms of 0, 1, 2, 4. F2 equal to ABC equal to sum of minterms of 0, 5, 6, 7. So what is the first step? You have to simplify by grouping the ones and by grouping the zeros. So I think all of you familiar with K-map. I am not going to detail about how to get the F1 and F1 bar, F2 and F2 bar. F1 by grouping the ones, F1 bar grouping the zeros, right? For zeros 3 pairs are there, for ones 3 pairs are there. So for every pair its corresponding product term. Similarly F2 and F2 bar. Then what is the second step? So we may consider F1 and F2, or if we may consider F1 and F2 bar, F1 bar F2, F1 bar F2 bar, right? In which choice we can get the less number of distinct product terms we have to identify. So you can clearly observe here F1 B bar C bar, A bar B bar, A bar C bar, F2 equal to A bar B bar C bar, AC AB. So total how many distinct product terms are present? Any repeated product terms or any common product term presenting in F1 and F2? No, all are distinct product terms. So what is the count in F1 and F2? F1 and F2 count is 6 distinct product terms are there. F1 taken in complement form, F2 in normal form. Just observe AC, BC, AB, A bar, B bar, C bar, AC, AB. So how many distinct product terms are there? What are the product terms are commonly covered by the F1 bar and F2? AC covered, then AB covered. So total how many distinct product terms are there? 1, 2, 3, 4 only. Next, F1 and F2 bar consider. F1 and F2 bar. So total how many distinct product terms are there? 1, 2, 3, 4, 5, 6. Right. Then F1 bar and F2 bar. So here how many distinct product terms are there? 1, 2, 3, 4, 5, 6. All are different, right? No. So here which choice you have to consider? Choice which is having less number of distinct product terms. So you have to consider the F1 bar F2. F1 bar F2 is the preferable choice to get the less number of product terms, right? How many AND gates? 4 AND gates. The PLA programming table list out distinct product terms AB, AC, BC, A bar, B bar, C bar. Inputs you have to list out, outputs you have to consider. Inputs A, B normal, so that's why you have to put a 1. C not present in the product, so you have to put a dash. So similarly you have to fill input column, right? Here observe A bar, B bar, C bar. So presence of A complement, that is 0. Presence of B 0. Presence of C also 0. Right now F1 and F2 you have to consider. F1 covers AB, so put a 1. Covers AC, covers BC, so put a 1. F2 AB, AC, BC not covered. A bar, B bar, C bar covers, right? So if it covers put a 1, not covers put a dash. So F1 taken in which form? Complemented form or normal form? F1 taken in complement form to get the less number of product terms. So that's why you have to mention F1 taken in which form? Complemented form. F2 taken in normal form, that is true form, right? Here how many AND gates required, how many distinct product terms are there? 4 product terms are there. That's why you have to consider the 4 AND gates. How many inputs are there? 3 inputs are there, A, B, C. So 6 lines you have to draw. 3 lines for normal A, B, C. 3 lines for complementary inputs A bar, B bar, C bar. Just you have to draw the one horizontal line which joins all 6 vertical lines, right? So to get the A, to get the 1, 2, 3, 4, what is the first product? First product, observe AB, right? Which fuses you have to make a connection? A, then B, right? Then what is the second product? AC, A, C. What is the third product? BC. What is the B line? This is the B line. Then what is the another C line? This is the C line. Next, A bar, B bar, C bar. So A bar line, B bar, then C bar. This is about programming of array of AND gates. Array of AND gates. Now this slot for programming the OR gates. 2 outputs are there, so 2 OR gates you have to draw. Then output we may consider normal form or we may consider the complementary form. So this setup is common. Fuse parallelly connected with NOT gate, right? So we are taking the F1 in which form? Complementary form. F2 taken in which form? True form, right? So whenever F2 taken in true form, this fuse connection you have to make, right? You have to directly consider expression is F2, so directly you have to pass. But here which one we are consider complementary, that is F1 bar we are consider to get less number of product terms. Otherwise we get the 6 product terms. 6 product terms means how many AND gates you have to take? 6 AND gates you have to take. So number of AND gates will increases, number of fuses are also increases. That's why to get the less number of product terms, different choices you have to consider, right? In this example we have to consider the F1 bar and F2. So here F1 bar is realized, but we require the F1. So F1 bar passed through NOT gate, so we can get the F1, right? So for that, what is the status of a fuse? Fuse should be open. Why the fuse closed here? Taken form of the F2 is true, that's why fuse is connected. Here taken form of the F1 is complement to get the less number of products, that's why fuse not connected. Signal expression output variable passed through NOT gate, so already we have taken F1 bar. If that is passed through NOT gate, we can get the F1, right? So then programming of OR gates consider. F1 bar covers first product, second product, third product. F2 covers first product, second product, fourth product. Just observe the table. Just at corresponding position, just to put a tick mark or cross mark, right? Cross mark you have to put, right? So only one thing, at output side you have to observe. If you are taken the complement, fuse open. If you are taking the normal, fuse closed, right? So this is about how the given switching functions can be designed with help of PLA. So every part is same, right? So the concept as compared to PROM is same. In a PROM, in this slot we are using the decoder. Decoder is also having the number of AND gates. Every AND gate having the all combinations of inputs, right? So but here selected number of AND gates are taken, so that's why the hardware is reduced in this slot, right? So how many number of fuses are there? Let number of inputs are n, number of AND gates are k, number of OR gates m, right? So in terms of nkm, total number of fuses, right? So here each AND gate having how many number of fuses? 2n number of fuses. 3 inputs are there, so 3 fuses for normal, 3 fuses for complement. So every AND gate having how many number of fuses? 2n number of fuses. Like this, how many AND gates we are having? K number of AND gates. So here how many fuses are there? 2n into k. If you observe, here total how many number of fuses? 6. Here 6. Here 6. Right? Total 4 AND gates. So in this, how many fuses are there? 6 into 4. 24 fuses are there. In generalized, how can you represent the total number of fuses at array of AND gates? 2n into k. Now every OR gate consists of how many number of fuses? K number of fuses, right? So here how many number of fuses are there? M into k number of fuses are there. M into k. M is the number of OR gates. Number of OR gates. 2 OR gates are there. Every OR gate having how many fuses? 1, 1, 2, 3, 4 fuses are available. But we are making the 3 fuses to get the only 3 products, right? 4 are available. Every intersection is the 1 fuse. Which fuses are connected to get the F1 bar? Right? Fuse connected to first AND gate, first product term. Second fuse, third fuse are connected. Fourth not used, right? So total how many fuses are there? K number of AND gates are there. So K number of electrical fuses are available for every OR gate. So here how many OR gates are there? M number of OR gates are there. So total how many number of fuses are there? M into K number of fuses are there. Here how many fuses are there? Here 1, here 1. So that means every OR gate having 1 fuse at output. So if M number of OR gates are there, how many number of fuses are there? M number of fuses are there. So therefore total how many number of fuses? At array of AND gates, 2n into k. At array of OR gates, m into k. At output side, m number of OR gates, right? So this is the expression of total number of fuses in which programmable logic device? Programmable logical array, right? So very simple concept. So this is about PLA.